You know that little clip on your pen? The one that always seems to snap off at like the worst possible moment?
Oh, yeah. Annoying.
Or maybe you've heard about those huge cargo ships. Back in World War II, they broke apart. Right in the ocean.
It's pretty wild, isn't it? Thinking that something seemingly so basic, just the choice of material, can lead to, well, small annoyances or genuine catastrophes.
Absolutely. And it's quite likely that you, listening now, have looked at something and thought, why this material for that job?
Yeah, maybe you're trying to fix something, or maybe just curious.
Well, this deep dive should give you a bit of a shortcut to understanding the real thinking behind those choices.
Exactly. Today we're diving into the really fascinating world of engineering materials.
We've got this fantastic resource. It's a pretty comprehensive book, actually. Really unpacks material properties, their limits.
And how engineers actually decide which material to use for what. It's quite detailed.
It really is. Covers everything, from how much something stretches if you pull it.
Right through to why things might break down after being stressed repeatedly, or how they corrode over time.
Yeah, and our source here, it's a great introduction to the whole field. What I like is that it doesn't just throw facts at you.
No, it uses real-world case studies and examples, lots of worked examples to show you how these ideas work in practice.
Makes it much clearer. So our mission today, really, is to pull out the key insights from this book.
Give you a solid grounding in how engineers think about material selection.
And hopefully uncover some, surprising facts along the way.
Should be interesting.
Okay, let's get into it. Why is understanding these material properties?
Yeah.
Why is that so absolutely vital for designers?
Well, the simple truth is, if you don't understand them deeply, things can go very, very wrong. Disastrously wrong sometimes.
Right.
Designers have to know about things like elastic modulus, that's stiffness, basically.
How bendy something is.
Or how resistant it is to bending, yeah. And fracture toughness, how well it resists cracking, corrosion resistance, loads of things.
And not just what they are, but where the limits lie, presumably.
Crucially, yes. Where are the limits? Because every material has them.
And the book really hammers this home with some, pretty shocking examples, doesn't it?
Yeah.
Those welded ships in WWII.
Exactly. They weren't always being sunk by torpedoes or bombs. Some just failed, broke into...
Just fell apart.
The steel they used, particularly around the welds, it just didn't have enough fracture toughness. Not at the cold ocean temperatures they were operating in.
So a tiny crack could just...
run right through the structure, catastrophically fast.
Right.
Yeah. And the book also mentions the early de Havilland comet crashes, the first passenger jet.
Ah, yes, I've heard about those. Fatigue, wasn't it?
That's right. Insufficient fatigue strength in the aluminum around the window frames. The constant depressurized cycle of flying hung.
Stressed it again and again.
Until cracks started at the corners of those square windows and just grew. Eventually, the fuselage just failed midair.
Chilling. Really shows that picking a material isn't just about, what's cheap or easy to get.
Not at all. And the source stresses that knowing these properties exist isn't enough. Designers need to know how they're measured. They need reliable data.
To actually solve problems with.
Right. And it also connects it back to basic science, physics, chemistry. Understanding why materials behave the way they do helps us improve them.
And it sounds like the book makes this practical, not just theory.
Definitely. The case studies are key for seeing it in the real world. And the worked examples. Some are straightforward calculations, but others are what the book calls divergent.
Divergent, meaning?
Meaning they encourage you to look at everyday things differently, like why does a traffic light pole bend a certain way in the wind? It makes you think like an engineer about the material choices involved.
I like that. Thinking like an engineer. Okay, so beyond the core properties, the book touches on broader stuff too, right? Like how we use materials as a society.
It does, yeah. Quite early on, it talks about use patterns and ubiquitous materials, the ones that are just everywhere.
Plastic, steel.
Exactly. And it points out the exponential growth in how much stuff we consume. Compare now to 50 years ago, it's staggering.
Which immediately raises a big question, doesn't it? Resources. Can we keep this up?
That's the critical issue. Are we going to run out? The book mentions that for quite a few really important materials, things like silver, tin, tungsten, zinc, lead, platinum, even oil, which is the basis for so many plastics. The estimated lifespan of known economically recoverable reserves is, it's within a typical human lifetime.
Wow, that's actually quite sobering.
It is. Makes you think about consumption, recycling.
Definitely. And the energy needed to get this stuff in the first place.
Right. The source touches on that too. The future of materials, finding substitutes, recycling, and the massive energy cost of extraction and processing.
Okay, let's dig into some of those fundamental properties then. The book starts with stiffness, you said. Sounds simple, but I guess it's crucial.
Incredibly important. Stiffness is all about a material's resistance to being deformed elastically.
Elastic.
Yeah.
Meaning it springs back.
Exactly. It springs back to its original shape when you remove the force. Young's modulus is the specific measure for this when you're pulling or pushing in one direction.
So like a rubber band versus a steel bar.
Perfect example. Rubber band. Low Young's modulus stretches easily, floppy. Steel bar.
Yeah.
Very high Young's modulus, very stiff, hardly stretches at all with the same force.
Okay. And to really get stiffness, we need to understand stress and strain first.
Yes, those are the building blocks. Stress is basically the force applied over a certain area. It's like the internal pressure within the material.
Okay.
Strain is the measure of how much the material deforms in response to that stress, like how much its length changes compared to the original length.
Got it. Force per area is stress, deformation is strain.
And Young's modulus is simply the ratio between them, stress divided by strain, but only in that elastic region before it starts to deform permanently.
So it tells you how much stress it takes to get a certain amount of strain, essentially.
Exactly. How much it resists deforming under load. And the key thing is, even materials that seem similar can have vastly different stiffness. Huge implications for design.
Makes sense. High stiffness means high resistance. But you mentioned sometimes high stiffness isn't what you want.
Right. Think about climbing ropes. You use steel wire sometimes for protection points. Steel is super stiff, doesn't stretch much. Now, if a climber falls, that lack of stretch means the impact force is transferred very suddenly, very harshly.
Ouch. Could cause injury. Or even break the rope.
Potentially, yes.
Yeah.
Or rope with lower stiffness, more stretch, can absorb more of that impact energy. It makes the fall softer, safer.
Right.
And conversely, think about rubber again. Its low stiffness, its ability to stretch a lot and return, that's exactly why it's useful for seals or shock absorbers.
So it's horses for courses. Matching the stiffness to the job.
Precisely. It's all about the application. And the source provides tables of Young's modulus for lots of materials and looks at related things like how beams bend or how thin things can buckle under compression.
And this tuning fork example, how does that work?
It's pretty neat. It shows you can calculate Young's modulus for steel just by knowing the fork's dimensions, its density, and the musical note it makes.
Really? From the sound?
Yep. The frequency, it gives the numbers. 440 hertz, that's an A note for an 85 millimeter long fork, 3.86 millimeters square cross-section. Steel density, 7.85 times 10 to the 3 kilograms per cubic meter.
Okay.
And it walks through the calculation. You get about 204 giganewtons per square meter. It's a cool way to see how these fundamental properties govern even simple objects.
Using sound to measure stiffness. Clever. Okay, so that's the big picture behavior, but what's happening right down at the atomic level? How do atoms sticking together dictate all this?
Now we're getting fundamental. The source explains it comes down to two main things. How the atoms are bonded, the forces holding them together, and how they're packed or arranged.
Bonds and packing.
Right, you've got strong primary bonds, ionic, covalent, metallic, holding atoms tightly.
Like in metals and ceramics?
Yes. And then weaker secondary bonds, van der Waals forces, hydrogen bonds, which are more important between molecules, like in plastics. The strength of these bonds is key.
Could you give an example, maybe ionic bonding?
Sure. Think table salt, sodium chloride. One atom, sodium, gives an electron to chlorine. You get a positive sodium ion and a negative chloride ion.
Opposites attract.
Exactly. Strong electrostatic attraction. But it's not directional. Like, the ions are like charged spheres. They just pack together efficiently, positive next to negative.
Okay. How's that different from metals?
Metals often use metallic bonding, which is more like a sea of shared electrons holding positive ion cores together. And they tend to pack very efficiently, like stacking cannonballs as tightly as possible.
Close packed structures.
Yeah, different ways they can stack, giving different crystal structures, but generally very dense because they fill space so well.
And polymers.
Yeah.
Plastics. They're less dense, usually.
Right. Polymers are long chains. Strong covalent bonds within the chains, but the chains themselves are often held together by those weaker secondary forces.
So the chains don't pack as neatly.
Generally, not as neatly or tightly as metal atoms. Plus, they're made of lighter atoms, carbon, hydrogen, oxygen mostly, so lower density. The book has a table, 5.1, showing this clearly. Copper is nearly 9 milligm, magnesium 1.74, polyethylene down around 1, wood even less.
That density difference alone must be huge for design.
Massive. And the stiffness of the bonds themselves. Table 6.1 in the book lists some that links directly to the overall Young's modulus we measure. Stiffer bonds generally mean a stiffer material.
Okay, so connecting the micro to the macro. How do engineers apply this understanding of modulus in actual designs? Where is stiffness the main driver?
The book has a great chapter on this. One key case study is racing yacht masts.
Yeah. Needs to be stiff and light.
Exactly. Maximum stiffness to transfer wind power efficiently, minimum weight for speed. It compares aluminum alloys with CFRP carbon fiber reinforced plastic.
Carbon fiber, that's the fancy stuff.
It is. Performance-wise, it's way better. Huge weight saving, maybe 5 times lighter than aluminum, sometimes more, and super stiff.
But there's always a but.
Cost. CFRP is maybe 30 times more expensive than the aluminum alloy.
Ouch. Okay, for Formula One yachts, maybe not for my weekend dinghy.
Precisely. It's a performance versus cost trade-off.
And telescope mirrors. Why is stiffness critical there?
Well, for really big telescopes, the mirror itself gets incredibly heavy, and the cost of the whole structure supporting it skyrockets with weight.
So you want stiff but light again.
Exactly. Maintain that precise mirror shape under gravity, but minimize mass. The book talks about modern solutions using segmented mirrors or large, thin mirrors with active control systems.
Active control, what's that?
Tiny actuators on the back push and pull subtly to correct any distortion from gravity or temperature changes, basically using tech to overcome material limits.
Wow. Compensating for the material? And then, the Challenger disaster. How did material properties, specifically elasticity, factor in there?
It was tragic. It wasn't stiffness exactly, but the elastic recovery of the rubber O-rings in the booster joints, how quickly they sprang back after being squeezed.
Right, they form a seal.
Yes. But the launch morning was unusually cold, and that cold made the rubber much less resilient, much slower to spring back.
So it didn't seal properly.
It didn't seal quickly enough when the pressure built up at ignition. Hot gas escaped past the O-ring, and the rest is history. Feynman's famous demonstration with the O-ring in ice water really showed it.
A chilling reminder how a basic material property under specific conditions can be absolutely critical. Okay, so we've covered elastic behavior. What happens when you push harder, beyond the elastic limit?
Right, now we're into permanent deformation. Plasticity. The key property here is yield strength.
That's the point of no return, where it stays bent.
Exactly. The stress at which plastic flow starts. Then there's tensile strength. It's the maximum stress it can take before it starts necking, thinning down.
Like pulling taffy.
And eventually breaks. You measure these typically with a tensile test. Pull a sample, record the force versus how much it stretches.
And the book mentions true stress and true strain. Why the distinction?
Well, as you pull the sample, it gets thinner, right? Its cross-sectional area decreases.
Here.
Nominal stress and strain use the original area and length. True stress and strain account for that changing area, giving a more accurate picture of what the material itself is experiencing, especially during large deformations.
Okay, a more precise measure. And work hardening. You can make metal stronger by bending it.
You can. When you deform a metal plastically, you actually make it harder and increase its yield strength. It's a common strengthening method.
How does that work? Why does it deform permanently in the first place?
On the microscopic level, it's down to tiny defects in the crystal structure called dislocations. Think of them as imperfections, like a ruck in a carpet. Okay. These dislocations can move relatively easily, allowing layers of atoms to slip past each other at much lower stresses than you'd need to break all the bonds in a perfect crystal.
So plasticity relies on these moving defects.
Yes. And strengthening methods often work by making it harder for these dislocations to move. You can put obstacles in their way, like tiny particles that's precipitate or dispersion strengthening.
Or work hardening does that too.
Yes, work hardening creates more dislocations and they get tangled up, hindering each other's movement. Making the crystal grain smaller also works grain boundaries, block dislocations. That's the Hall-Petch effect.
Lots of ways to toughen metals up.
Definitely. The book also briefly mentions creep.
Creep.
Yeah, slow, time-dependent plastic deformation. It happens under constant load, especially when things get hot, like a turbine blade in a jet engine slowly stretching over time.
Okay. So even if the stress isn't high enough to yield it instantly, heat and time can still cause permanent deformation. Important for high-temp applications. Now, what about when things break completely? Fracture.
Right, fracture mechanics. This deals with how cracks start and grow. The key property is fracture toughness, K sub C usually. It's the material's resistance to crack propagation.
Okay. And there are different ways things break.
Broadly, yeah. Ductile fracture involves tearing lots of plastic deformation before it finally breaks. Think pulling a ductile metal rod apart.
It necks down, stretches.
Exactly. Brittle fracture is sudden, rapid crack growth with very little deformation. Think shattering glass.
Much more dangerous usually.
Often, yes, because it's sudden. And fracture toughness isn't fixed. Temperature is a huge factor.
Like those WWII ships again.
Precisely. Some metals get much more brittle when cold. Their fracture toughness drops. Microstructure matters too, the grain size, any inclusions.
And for brittle materials, tiny flaws are a big deal.
A huge deal. The book explains that their actual tensile strength is often governed by the size of the biggest microcrack or flaw already present. There's even an equation. Strength is roughly proportional to fracture toughness divided by the square root of the flaw size.
So even tiny invisible flaws dramatically weaken brittle stuff.
Yes, which leads to variability. That's why the book introduces the Weibull distribution.
That sounds statistical.
It is. Because flaws are random, the strength of brittle materials is statistical. Weibull analysis helps predict the probability of failure. The Weibull modulus measures the variability. Low like chalk means lots of variation. High like good ceramics or steel means more consistent strength.
So you need to design for the weakest possible piece, almost. Okay, so that's breaking under one load. But things also break from repeated loads, right? Fatigue.
Yes, fatigue, the silent killer, sometimes called. Failure under repeated or cyclic loading, even if the stress each time is way below the material's normal breaking strength.
Like the Van Pen clip.
Exactly, or a bicycle pedal axle snapping after thousands of miles. It's sneaky because there's often no warning.
And they're different types.
Yeah. High cycle fatigue is lots and lots of cycles, millions maybe, at low stress. Think vibrations. Low cycle fatigue is fewer cycles, maybe hundreds or thousands, but at higher stress levels that cause some plastic deformation each time.
How do engineers predict this?
They use SN curves, stress versus number of cycles to failure. Plot the stress range, apply it against how many cycles it lasts. Tells you the fatigue life at different stress levels.
Can you make things more fatigue resistant?
Oh, yes. Surface finish is critical. Scratches are stress concentrators where cracks love to start.
Like the corners of those Comet windows.
Exactly. Sharp corners, holes, notches, all bad for fatigue. Smooth transitions are much better. You can also introduce compressive stresses at the surface.
How does that help?
Fatigue cracks usually grow under tension, pulling things apart. If the surface is already squeezed together under compression, it counteracts the applied tension, making it harder for cracks to open and grow. Shot peening is a common way to do this.
Blasting it with little balls.
Basically, yeah, it puts the surface into compression.
So the Comet failure was a huge lesson in fatigue.
Absolutely. Led to rounded windows, much more rigorous fatigue testing. The book also mentions the Ascheto train crash in Germany, possibly linked to fatigue in a wheel design, and the old Tay Bridge disaster wind loading plus stress concentrations in brittle cast iron lugs. Fatigue and fracture are major concerns.
Definitely seems that way. Okay, let's shift gears. Another big failure mode. Corrosion. Things rusting, basically.
Well, rusting is one type. The book distinguishes between dry oxidation reacting with oxygen, usually at high temperatures.
Like scale forming on hot steel.
Right. And wet corrosion, which is more common. It's an electrochemical process. Needs water or some conducting liquid electrolyte.
Electrochemical, like a battery.
Sort of, yeah. You get different areas on the metal surface acting like tiny electrodes. Anodes, where the metal dissolves, losing electrons, and cathodes, where another reaction happens, usually consuming oxygen or producing hydrogen, taking up those electrons.
Fascinating. A tiny electrical circuit causing damage.
That's the idea. The book mentions Porbet diagrams, too.
Sounds complex.
They look complex, but they're basically maps showing which form of a metal, the pure metal, an oxide layer, or dissolved ions is stable in water at different electrical potentials and pH levels, acidity. Helps predict if corrosion is likely.
So you can see the danger zone.
Kind of. And it also highlights localized corrosion, which can be nasty.
Localized.
Instead of uniform rusting, the attack focuses on small areas, pitting tiny deep holes, intergranular attack corrosion along the grain boundaries inside the metal, stress corrosion cracking, where you need both tensile stress and a corrosive environment for cracks to grow.
Sounds bad. How do we stop it?
Several ways. Choose a more resistant material, like stainless steel. It forms a protective chromium oxide layer. That's pass protection.
What else?
Coatings, paint is the obvious one, or plating with another metal, like galvanizing steel with zinc. The zinc corrodes preferentially, protecting the steel.
Sacrificial protection.
Exactly. Or you can use cathodic protection. Connect the steel structure, say a pipeline or ship hull, to a more reactive metal block magnesium or zinc often. The block becomes the anode and dissolves, protecting the steel cathode. Or impress a current to force the steel to be the cathode.
Clever tricks. Okay, one more degradation process. Friction and wear. We deal with friction every day.
We do. The book covers the basic static friction holding things still, kinetic friction resisting movement, and the slightly weird laws of friction.
Weird how?
Like friction force being largely independent of the apparent contact area. You'd think a wider tire grips more just because it's wider, but the basic physics says area doesn't matter much.
That is counterintuitive. Why?
Because surfaces aren't smooth microscopically. They touch only at the peaks, the asperities. The real contact area is tiny, much smaller than the apparent area.
So it's the pressure at those tiny points that matters.
Right. Friction arises from shearing the tiny welds or junctions formed at those real contact points. And the real area is proportional to the load pressing the surfaces together.
Okay, that makes more sense. What affects friction then?
The materials involved, obviously.
Hmm.
Any surface films, oxides, contaminants, and lubrication, of course, putting a slippery layer between the surfaces.
Any case studies here?
Yep. Journal bearings and engines need materials that carry load but can also deform slightly if needed. Skis and sledge runners minimizing friction on snow using things like polyethylene or Teflon.
Like slippery stuff.
And the opposite high friction rubber for tires, where you want maximum grip. It's all about managing those surface interactions.
Fascinating how it applies both ways.
Yeah.
Okay, we've covered a lot. The last big topic was materials and energy in car design. Why focus on cars?
Well, the car industry uses vast amounts of material, and it's under huge pressure to change.
Sustainability, fuel efficiency.
Both. Growing environmental awareness, stricter emissions regulations, fuel costs, they all push towards lighter, more efficient vehicles.
So moving away from just using steel.
Exactly. Looking at lighter alternatives. Aluminum alloys, magnesium alloys, composites GFRP, glass fiber, and CFRP, carbon fiber.
The same CFRP as the yacht masts.
Yep. The goal is weight reduction. Lighter car means less fuel burned, lower emissions, simple physics.
But you can't just swap steel parts for aluminum parts of the same size, can you?
Usually not, no. As we said, materials have different properties. Aluminum is less dense than steel, but also less stiff for the same thickness.
So same size aluminum panel would be too floppy.
Potentially, yes. So engineers have to redesign the parts, use clever shapes, maybe slightly thicker sections in places to get the needed stiffness and strength, but still save weight overall.
More complex than it sounds.
It is. And you have to consider manufacturing, too.
Yeah.
How do you join aluminum parts? Can you stamp it easily? What about cost? And recycling. Lots of trade-offs.
And the energy involved. Not just fuel saved, but energy to make the materials.
Right. The book touches on that life cycle energy. Making aluminum takes more energy than steel, but you save fuel over the car's lifetime. It's a complex balance. Cost, performance, manufacturability, environmental impact.
It really sounds like car design is right at the intersection of all these material challenges.
It really is a constantly evolving field.
Well, this has been quite the journey, from atoms bonding up to cars and planes. It's amazing how much deep science underlies seemingly simple choices.
Absolutely. And hopefully you, the listener, now have a new lens to look through. When you see an object, think about the material. Why that one? What properties were critical?
Yeah, think back to those failures we discussed, the comet, the ships, even that pen clip. Why did they fail?
Right.
Was it the wrong material? Or maybe used outside its limits?
Exactly. Understanding the why behind material choices and failures is key.
So here's a final thought to leave you with. As we develop even newer materials, maybe things with self-healing properties, or incredible strength-to-weight ratios we can barely imagine now, what current limits might we overcome? What totally new designs might become possible? Think about everyday objects or complex systems.
Or flip it around. Think about sustainability. As that becomes even more critical, how will the need for environmentally friendly materials, easy recycling, low energy production, how will that completely reshape the materials palette engineers have to work with in the future?
Good question. Maybe look around you right now. Pick an object. What's it made of? Why? Perhaps this deep dive has sparked your curiosity to find out more about a specific material or how something you use every day is designed.